Good morning. We are covering Geometry Lesson 6.5 on isosceles and equilateral triangle congruence. And so we're going to be able to recognize and prove that if a triangle has two congruent sides, its third side, called the base, will form two congruent angles where the base joins each of its congruent sides. So that's an isosceles triangle. And then we'll also be able to recognize and prove that if a triangle's three sides are congruent, then its three angles are congruent. And these are the same triangle, but if we're talking about the three angles, it's called an equiangular triangle. And if we're talking about the three sides, it's called an equilateral triangle. This supports geometry skills K9 and K10 in IXL. Make sure that you take notes on this. You upload them to me by 11:59 p.m. Saturday. You can either do them by Student View Dropbox or by my email, and make sure you include the header if you want full credit. All right. So here we're looking at the properties of isosceles triangles. So a triangle is isosceles if it has two congruent sides. So here's a picture of an isosceles triangle, and you'll see the two legs are congruent. They have tick marks showing it, and they're called the legs. The third non-congruent side is called the base, and the base is always opposite the vertex angle, which is up here. Okay. So now, why are the two base angles congruent? So the way we show this is by virtue of a little construction. I drew this little triangle, and it's an isosceles triangle, and cut it out. Why is it isosceles? Because the two sides, you see, have little tick marks on it showing that they're congruent. And indeed, I did this very carefully so that it would do that. Now, to show that these two angles are congruent, all I did was fold them down the middle of the vertex. So in other words, I created an angle bisector, and I did this. And when I did that, you'll notice you can see the angle, and bleeds through both sides, okay, in the same spot. Now this one's a little tougher to see. I don't know if you can, but the angle's there, and you can sort of kind of tell by looking at it that yes, indeed, these two are congruent. Now, what really tells it to you is, you know, if the two halves of the triangle form or lie right on top of each other, like they do here, okay, you've got all the parts of the triangle have to be congruent, okay? And so that's called corresponding parts of congruent triangles are congruent. This is an illustration of that. Real quickly, just showing you with a, these are little tiles, but if I were to, gotta get these in the right spot. If I were to take these two and put them together, it forms an isosceles triangle. This is not quite equilateral. Not quite equilateral. But even if for both of those kinds of triangles, you can fold them over like that, and they form one triangle. So that's telling you again, all the corresponding parts of each side are congruent. Each triangle are congruent, I should say. But they're the side of one larger triangle because they make one triangle. Okay. All right. So that's a very simple explanation of what's going on. Let's just go through and address the theorem. So a theorem was developed based on this information. And so it's called the base angles theorem. And it says if two sides of a triangle are congruent, then the opposite angles on the base are congruent. The angles opposite them are the base angles, okay? And so if side AB is congruent to side AC, then angle B is congruent to angle C. That's what it's telling you. The converse of the base angles theorem is you could start out with the angles and conclude that the that the legs are congruent. So if two angles of a triangle are congruent, then the sides opposite them, these sides AB and AC, are congruent. And so I marked them that way. And here is the statement that says that. Okay. Okay, now I started this actually previously, and I discovered I wasn't recording properly, so I had to re-record. But I'm going to use what I used before because all the information on it is good. So, example 1, proof of the base angles theorem. So we're going to actually do a proof of that theorem that we were talking about. So we're given a triangle ABC. We are told that the sides AB and AC are congruent. We want to prove that the base angles B and C are congruent. Okay, so what I did here was a paragraph proof. So we said draw the bisector of CAB. So bisector of CAB, what are they talking about? Angle CAB. CAB. They're talking about the vertical angle up here, A, which we would just call A, but it's CAB, angle CAB. And the bisector is this blue line that's through here. And by construction, angle CAD, this angle at the top, I'm sorry, the angle at the bottom, CAD, and angle BAD, the one at the top, so this one here and this one here are congruent. Simply, this is what we saw here. With this vertical angle, the two little angles on each side are congruent simply because you fold them over and you see, oh yeah, they're congruent. Okay. So you are given that information, and then you're also given that, that side AB is congruent to AC. So this and this, we said were congruent. Now, DA is the angle bisector here, that bisects the vertical angle. It's congruent to itself by the reflexive property. And so I put 2 tick marks there. It's the reflexive property of congruence. And so then we can use this congruence to conclude that the 2 triangles are congruent. Why? Because we have side angle side, side angle side. We can prove they're congruent. And therefore, now when I say side angle side, I've got a side here, A, B, this part of the vertical angle, which is angle BAD, okay, this little one up here, and this side, they're all congruent. And then over here on the lower triangle, again, I have the side AD and side AC are congruent. I'm sorry, they're congruent to the other sides of the other triangle. And you have this angle. So I've got side angle side, side angle side. The 2 triangles are congruent. Now, B and C, we had not up until this point talked about them, but because they are parts of these 2 congruent triangles ADB and ADC, then we can conclude using CPCTC that the base angles are congruent. So what is CPCTC? It's a huge shortcut. It means that corresponding parts of congruent triangles are congruent. Okay? This is a big one that you'll want to keep in your quiver of arrows of things that you can use to shoot down all your problems. So again, as long as you can prove that 2 triangles are congruent, then you can prove something else about the triangles that you hadn't talked about before are also congruent using CPCTC. Corresponding parts of congruent triangles are congruent. Okay, last one. Nope, not quite. Almost last one. There's a corollary to the base angles theorem, and that is if and a corollary is just kind of a little offshoot proof. Okay, so if a triangle is equilateral, and this triangle here is equilateral AD, then it is also equiangular. So meaning that these 3 angles are also going to be congruent. And then you can say it in reverse. If a triangle is equiangular, then it is equilateral. So since we know that these angles are the same measure, using the triangle sum theorem, you can conclude that angles A, B, and C have to equal 180 degrees. So if you just call them x, then 3x equals 180 divided by 3, and you figure out that each angle is 60 degrees. And that very quickly takes us into our last slide, which is using equilateral and isosceles triangles in a pair here to solve a problem. Okay, and we're going to do this as a two-column proof. So first of all, find the value of x. Now over here, we only had originally just this x that's sort of blue-green, but this was an equilateral triangle on this side. You'll notice the three sides are congruent, 3 tick marks. And so what I did was I said, okay, if that's the case, this is an equilateral triangle, then it's also equiangular. So I just wrote in the other two angle measures, which are x degrees as well. Now we don't know what x is at first. We just know that it's the same measure. So now using the triangle sum theorem, you can quickly conclude, as we did in the previous slide, that these three angles have to equal 60 degrees. So I just wrote that over there. So the shortcut, x degrees represents the measure of an angle that is part of an equilateral triangle. From the previous corollary, which I was just talking about, this triangle is also equiangular. Okay, and so knowing that, we were able to say that the three angles, the three x's unknowns, equals 180 degrees using the triangle sum theorem. And then we want to solve for x, so we divide by, oops, I said x, it's divide by 3. Divide by 3 on both sides. Okay? Let me just put a daub of white out in here. So we divide by 3. And on both sides, and of course, when you do that, you find out that your x equals 60 degrees. So we've just solved for x, which was what they asked us to do up here. And so now we've got the second triangle here. And you'll notice over here, it said y degrees, and it also showed that the two sides of the triangle over here and here were congruent to one another. So that means you've got an isosceles triangle here. And so with isosceles triangles, this is a base angle, and so this would be the other base angle, and since this one's y, this one has to be y. And then that one has to be the vertical angle, okay? All right, so we're going to do a little shortcut. Y degrees represents a base of the angle of an isosceles triangle. So the other base angle is the same measure. We said that. And then vertical angles forms the vertical angle up here forms a linear pair with this 60-degree angle that's represented as x degrees here. Okay, how do I know that? Well, you'll notice that if you turn this around, here you got the side here, and there's an angle here and an angle here, and they both share this leg here. So this is a linear pair. It's a linear pair. And linear pairs always equal 180 degrees. So, knowing that, 60 degrees plus the vertical angle has to equal 180 degrees. Now, let's go over and do our proof. So we'll take that, 60 degrees, plus the measure of the vertical angle equals 180 degrees. And that's the definition of a linear pair of angles. Now we'll just do a little math. We'll subtract 60 from both sides. And it's okay to mix math and little words here in geometry. We have no problems with that. We do that a lot. So that's subtraction property. And so we end up with the measure of the vertical angle is 120 degrees. So this is going to be 120. So this is 120 degrees. All right. So now that we know that, 120 plus the two y's has to equal 180 degrees according to the triangle sum theorem. Now let's solve for the y. So we subtract 120 from both sides, subtraction property. And we get 2y equals 60. And then we divide by 2 on both sides using division property. And that helps us solve for y. Because when we divide by 2, 60 divided by 2, 30 degrees. And we're done. Okay. So I know this is a bit of a busy slide. I'll go back up here and let you see the top part again. There it is. And then here's the bottom part. There it is. And of course you can start and stop this and rewind this video. This is not a very long video, and I hope you were able to get a bit more information on triangle congruence. One of the biggest ones being corresponding parts of congruent triangles are congruent. So long as you got some information that's enough to make your two triangles congruent, if you're comparing them, then you can get information on something else in one triangle and say that that's also congruent in the other triangle. Okay. Thank you very much, and have a good morning.